So in the last class, we were looking at the following setup, where there's a concept class H, which maybe has a small approximation error, a small estimation error, but finding the empirical risk minimizer could be very hard, right? So learning the concept class H is potentially difficult. On the other hand, let's suppose that we somehow have a base hypothesis class, let's call it B. So this is a simple hypothesis class where ERM can be done very efficiently, right? But the problem is, since B is very simple, firstly it may have a very large approximation error. So your class is not rich enough, right? But you can learn this class efficiently. So the approximation error may be large, and we need some way of reducing the approximation error. Okay. So when the true concept comes from this class H, we're not able to guarantee that ERM over B can give us a small generalization error. But what we are guaranteed is that ERM over the base class B gives you a probability of error that is less than half. All right? In fact, it's bounded away from by some particular gamma. So for every concept in H, there exists some base predictor HB which achieves a probability of error of less than half minus gamma, irrespective of what the true ground truth distribution is, and irrespective of what H is. All right, there's some constant gamma such that this can be achieved. And since there exists one such H, ERM is going to find that particular, the hope is that your ERM is going to find that particular HB. So our goal is to somehow combine predictors from the base hypothesis class to produce a strong learner, one which can, let's say, at least achieve a training error that is close to zero. Okay, that's going to be our agenda. All right, because so let's suppose that the data is generated according to the concept class H, according to this particular H. If you take any particular base predictor HB, the training error that this achieves is less than half minus gamma, but could be close to half. Okay. So is there a way of somehow combining base predictors to give a more complex predictor which achieves a vanishingly small training error? We'll not worry about what the test error is, but at least it should achieve a small training error. And so to understand that, let's look at a simple base class. So let's suppose that the hypothesis class that we have, from where the concepts are generated, so the concept class is the set of all predictors of this particular form. Right? So this is indicator X being between alpha and beta. So it labels everything less than alpha to be 0, everything greater than beta to be equal to 0, and everything between alpha and beta to be plus 1. Or let's say minus 1 in this region and plus 1 in this region. Okay? But the base class is the set of all threshold classifiers. So it's indicator greater than or equal to theta, or indicator less than or equal to theta. All right, those are the kind of, that's my base class. So the question is, can you combine these, can I somehow combine, whatever it means to combine, can I combine base classifiers to produce a much more complex classifier? All right, and one such way of combining base classifiers is what is called bootstrap aggregation, also referred to as bagging. So to understand this, let's again take the base classifier.
So I have a doubt in the definition of when we define the base class.
Okay.
When we said that there exists a computational effective base gamma weak learner, I think the condition is a bit misleading.
Why do you say misleading? Which part?
Like, here,
Okay.
the second statement shouldn't be like this, that there exists a gamma weak learner in the base class.
Exactly.
But then why are you written that for any h belonging to h, there exists some base vector hb? So what is the relation between h and hb?
So I'm assuming that the ground truth is coming from H,
Okay, so that's the
right? That's so with respect to this ground truth, I'm restricting the ground truth, right? I'm not asking for an agnostic gamma weak learner. I'm asking for a gamma weak learner for this concept class. Okay, that's all that I'm requiring at the moment.
HB should belong to the base class.
So HB belongs to the base class, but H is my concept class.
Which may not belong to the B. Which may not belong to B.
Which is in general, HB is not going to belong to H.
You don't say H also may not belong to B, the true function.
Or H may not, yeah, in general, H is not going to belong to B. Yeah. Right? If H belongs to B, then you can achieve a zero training error.
Find a strong learner.
Yeah. You might as well get a strong learner. In this case, I'm assuming that we don't have a strong learner. All right. Okay, great. Okay, so to understand how we can potentially combine weak learners to give a strong learner, or something even more basic, can we combine simple classifiers to produce a more complex classifier, right? So let's take 3 classifiers.
This example gives the...
Yeah, so we'll just see that. So let's look at HB1, which is indicator, let's say x greater than or equal to theta 1. HB2 equal to, let's say, indicator x greater than or equal to theta 2. Maybe let me indicator x less than or equal to, x greater than or equal to theta 1, x less than or equal to theta 2. Let's say HB3 is indicator x say greater than or equal to theta 3. Well, let's say that this is one such collection, and for now let's simply assume that theta 1 is less than theta 2 is less than theta 3. I'm sorry? If HB3 is? Why is it? No, I'm just, okay, this is my class of classifiers, right? I just want to understand what this looks like, okay? So let's say that this is my theta 1, this is theta 2, less than theta 3 is minus 1 and plus 1. So there are 4 different regions. Let's suppose that we are trying to classify in the interval from 0 to 1. There are 4 different regions. If I take H to be, let's say, majority of H1b, H2b, H3b, then what does this classifier look like? So in the interval from 0 to theta 1, what is the labeling? So in 0 to theta 1, H1b is going to output -1 and H2b is going to output +1 and H3b is going to output -1. Alright, so here it's -1. And what happens in between theta 1 and theta 2? It is H1b is +1, H2b is also +1, H3b is -1. So this is +1. What about theta 2 to theta 3? So H1b is -1, H1b is +1, H2b is -1 and H3b is -1. Right, so this is -1. And for, let's say, H3 in the region from theta 3 up to 1, H1b is +1, H2b is -1 and H3b is +1. Right. So right now all I did was I took the base classifier, I just took a bunch of threshold classifiers and then I combined them using a majority rule. Alright. And I got this particular predictor which does not lie in the base hypothesis class. Right. So if I look at this new hypothesis class H prime, which is the set of all H, which can be written as, say, majority of H1b, H2b, H3b for HIB in the base hypothesis class. This is a much richer class than the base hypothesis class. Right? And I can make this hypothesis class richer just by increasing the number of base predictors I take to take the majority. So if I take the majority of, let's say, 5 base predictors, then potentially I get something more. Right? So right now you see this is great because now you can increase the richness of this hypothesis class, so you can reduce the approximation error. Right, but then how do you train this? Because in the end, I can't just do empirical risk minimization over this class. So the strategy behind bagging is the following. You have your data set S, right? From this S, you create new data sets just by resampling points from S itself. So you independently and with replacement, you sample n points or some n1 points from S to get a new data set S1, and then let's say you do ERM to get H1b. And from S, you again independently sample, again uniformly at random with replacement to get S2, perform ERM to get H2, and so on. You don't have any new data. It's still coming from the original data set S. Right? You're not getting any additional data points. You're resampling from the data set that is given to you. So you're reusing the data set over and over again. All right? So you get these predictors, H1b, H2b up to HKB, and then your final predictor is the majority of the outputs of these K predictors. Okay, at the moment, this is a very heuristic approach, right? Why do you even resample from the original data set again and again? And why should this work, right? Because now the data sets S1, S2 up to Sk, they are not distributed according to the original distribution anymore, right? Remember that S, the original data set, has points that are IID, say PXY, right? If you take, let's say, S1, now the points are not, if you take, let's say, S1 and S2, the points in S1 are not really independent of the points in S2. Conditioned on S, the points in S1 are independent of S2. But unconditionally, S1 is not independent of S2 because both of them are derived from the same data set S. Right? So this method of resampling from the given data in order to get a better algorithm, this is an algorithm called bootstrap. And was studied in the context of distribution estimation. We won't spend any more time talking about bagging specifically, but that's how bagging derives its name, bootstrap aggregation. All right. So that's one way, right? Basically the idea behind bagging was you have the data set, you resample to create from this data set S to create new data sets S1, S2, S3 up to Sk. You do ERM on each of these data sets to get H1b, H2b, and so on, and then you combine them through just a majority vote. All right. Boosting uses a modification of these ideas. In bagging, the idea was you independently sample S1, S2 up to Sk. The idea behind boosting, on the other hand, is the following. You have the original data set S. Yeah.
Before we leave backing, is there a result that in the previous, if the BC dimension of the base class is daily,
Uh-huh.
then if we apply majority voting, the BC dimension of the new majority basis class will grow as n O of n d log n.
I'm not sure about the exact relationship, but yes, as you increase both in bagging and boosting, as you increase K, the VC dimension also increases. Right? So standard VC dimension based techniques are not enough to prove generalization bounds on for bagging or boosting. You need other, say, margin based bounds to derive generalization bounds for both for bagging and boosting.
And then how can we capture the fact that complexity is increasing theoretically?
The complexity is
Richness
increasing. the richness is increasing. So as I said, the VC dimension increases as k increases. But which means that it's also harder to learn the class, right? So the generalization error can also potentially increase because the VC dimension keeps blowing up, right? So standard VC dimension based generalization error bounds are generally weak. They are not terribly informative. But you can derive margin based generalization bounds, which means that you look at this, let's say you look at this particular hypothesis class, which is now a richer class than your base class, and you assume that your data set guarantees a certain margin for this complex hypothesis class. And now through the process of bagging, boosting or whatever, you find out what is the bound on the generalization error. All right. So those are rather successful in giving reasonably good predictions. So this is a scenario where the traditional VC dimension, just Rademacher complexity approaches fail. All right. So coming back to bagging to boosting. So in boosting, the idea is the following. You are given a data set S. The idea is first you sample uniformly and with replacement. To get a new data set S1. To get a data set S1, and now given S1, you train, let's say you run ERM to find a predictor H1B. Okay. Now in bagging, what would you do next? You would again sample uniformly with a replacement from S to get S2. In boosting, the idea is instead of sampling uniformly with replacement, depending on how well H1B performed, you generate a new distribution. All right, so you have an original distribution P0, which is uniform. Now you change P0, you modify P0 to get a new distribution P1, and you sample from S according to the distribution P1, independently of S1, to get a new data set S2. And using S2, you, let's say, run ERM to get a new predictor H2B. Now, depending on how well H1B and H2B performed, you tweak the distribution P1 to give a new distribution P2. Again, sample according to P2 to give S3.
What is P0?
So P0 is a uniform distribution. I've not told you how you get.
From the data set.
You are uniformly sampling from the data set. Right? It's the same data set that I have. I'm sampling from the data set, but according to a different distribution. I'll explain that later, but this is sort of the high level approach. So I keep modifying this to get some PK. I'll sample to get SK.
Why would you expect something like this to work?
Yeah, it's not obvious why this should work. Right. So largely the intuition is behind how you modify P0, P1, P2, and so on. Okay, and the way and the intuitive way of explaining how you choose P1, P2, and so on is the following. So let's take a visual example to perhaps explain. Okay, even before that, so I get these predictors H1b, H2b up to HKB. In bagging, what you do is you take the majority of these, right? So, but in boosting, you instead take the sign of a linear combination of, or a convex combination of these HIBs. So alpha 1 H1b plus alpha 2 H2b, so on, alpha k HKB. No, I mean not for all alpha i's.
Can you choose some values of alpha such that this function is the majority?
Okay. I think so. Not indicated, right? You have to fix alpha 1, alpha 2 up to alpha k. Yeah, so let's take 3 of those. Then you take alpha 1 equal to alpha 2 equal to alpha 3, right? Let's take, say, h equal to sine of h1b plus h2b plus h3b, right? So now when is this positive? So each HIB can take values only +1 or -1, right? So this is positive only if 2 of them are +1. It's or at least 2 of them are +1. It's negative if at least 2 of them are -1.
So when bagging is basically you don't change the distributions.
Exactly. Yes. So bagging in that way, bagging is a special case where all of the alpha i's are equal to 1 and the distribution is never changed. All right. So in the general form, bagging is a special case of boosting. Okay, and the reason or the way you tweak the distributions to go from, let's say, P0 to P1 is that in P1 you give a higher probability to those samples that were misclassified by H1b. Right? So let's say that so originally you had S, you sampled from S according to the uniform distribution to get S1. Right? Now, over this you trained H1b, you got H1b. Now this H1b makes some errors in S1. The new distribution P1 is such that there's a slightly higher probability of picking those samples which were incorrectly classified by H1b. Let's say Pi of x or Pi plus 1 of x is larger than pi of x if x is classified incorrectly. By hi. So in other words, that's what the boosting algorithm is trying to do, is basically you're adaptively trying to find those samples which were wrongly classified by the previous classifier, and now you're trying to design a new classifier which does preferentially well over those samples. So if you see more samples from, if let's suppose that there's one sample x which was incorrectly classified by hi, right? Now, since there's a higher probability of sampling x than other samples, then the new data set that you generate definitely is going to have x with a higher probability, and maybe x will repeat. There's a higher chance of it repeating, which means that in your hi plus 1, there's a lower chance of making an error for x. All right. So that's the high level intuition. Okay. So let's look at at least visually. Let's try to see an example in 2 dimensions.
So you just said like since next time the exercise will have a higher chance and
Correct.
maybe we can operate multiple times.
Correct.
This means that it would have a lower chance of a better chance of being classified correctly.
Correct.
I-
In the new classifier, by the new
I didn't
classifier.
understand
I'm sorry?
I didn't understand this connection that since there is more probability, more number of times that misclassified sample will appear,
Uh-huh.
how does this increase the probability of it being classified correctly by the misclassified?
Because in the next step, let's suppose that you see a lot of samples. Suppose that x appears multiple times in si plus 1. Okay, right? So I have right. Let's start from the beginning. Suppose I have S0, right? And in S0, maybe let's take this example. Suppose let's take a case where my domain is, say, a box of unit length, right? A square box of unit length, and the original hypothesis class can be something complicated. Let's not worry about that. My base class consists of classifiers h of x1, x2, which take the form indicator xi, say, greater than or equal to theta. All right. Let's say either x1 greater than or equal to theta, or indicator x1 less than or equal to theta, or indicator x2 greater than or equal to theta, or indicator x2 less than theta. So essentially my classifiers are of the form where you pick a particular component, either the first component or the second component, and for that component you implement a threshold classifier. Right? So in other words, your classifiers are all the form where let's say you pick a particular theta and everything to the right of theta is labeled +1, everything to the left of theta is labeled -1, or for the same theta, everything above theta 1 is labeled +1 and everything below is labeled -1, and so on. Right? So only those kind of classifiers are allowed. So basically the decision regions are these kind of rectangular regions. Everything to the right of theta, or everything to the left of theta, or everything above theta, or everything below theta. Those are the only kind of decision regions that you can obtain. Now, suppose I now get some kind of data set which looks sort of like this. So these are labeled with one label. And these are labeled something else. Okay. Maybe let me pick this. Right. So now let's say that I run ERM to get one particular classifier. Okay. Suppose that the classifier looks something like this. I resampled points from this according to the uniform distribution, and then I trained a base classifier. Let's say that I get something that looks like this. Okay. So basically everything to the left of this line is going to be labeled brown, and everything to the right of this line is going to be labeled blue. So this is my H1. H1B. Now in this particular set of points, now let's see where H1B went wrong. So H1B classifies everything correctly except for this point and this point.
May I ask a question? Yeah. H1B since being computed by ERM.
I'm assuming that H1B is computed using ERM.
So it should obtain a zero training error. It should obtain zero training error.
You can't, right? How do you can you draw a line either horizontally or vertically?
Oh,
Because my base class is simple, remember? Right? That's the point. My base class is very simple. Right? In this case, if I had a more complicated class, let's say I allowed all kinds of hyperplanes in all orientations, then I could achieve zero training error and be done with it. But because I'm using this very simple base hypothesis class, I'm only allowing hyperplanes which are parallel to the x-axis or x1 axis or to the x2 axis. Right? So over this data set, I can't achieve zero training error. Okay. In particular, if I could achieve zero training error, then I might as well just stop. Okay.
How alpha 1 to alpha k design?
Which one? Alpha 1?
Alpha k.
We'll see that later. That's still a bit further ahead. Okay. And how you choose all of this depends on the variant of the boosting algorithm that you're considering. Okay. Right now, all I'm doing is just try to give intuition for this general philosophy. Okay. So here we see that this classifier has made errors on these 2 points. Right. So now you tweak the distribution such that the probability of getting this point, let's say either of these 2 points, is larger. Okay, so this is the original data set, but I've drawn these two a little thicker, which means that the probability of when I'm sampling S2, the probability of picking these points is higher, right? So when I sample the data sets, because I'm sampling with replacement, right? That's important. I'm sampling with replacement. In my new sample data set, maybe I observe, let's say, this point thrice, this point twice, and some of these points once. Okay? So my new sample data set, so this is the general picture, but let's say that but my data set, let us say, contains, so this is S, and this is my S1. S1 can contain multiple instances of some of these points and no instances of some of the other points. Right? So maybe S1 doesn't have this, whatever doesn't have, maybe doesn't have some of these points. Okay.
Why are you running ERM on S?
I'm sorry?
Why are you running ERM on S?
Why am I running ERM?
What's the first step?
So the first step was I ran ERM on S. I mean on S1, really, right? So this is, I want this to be sort of the global view. Okay, my bad. This should be S2. I'm drawing S2.
You have just decreased the number of samples.
I've decreased the number of samples, but maybe some points are represented twice.
But they would be at the same position.
They would be at the same position. That's okay. Right, so I have 3 points here, which are basically the same point repeated.
Wait, is that S or S1?
This is S2. So from S, I got S1 and trained this to get H1. I sort of skipped a step.
So he's asking what the leftmost is that?
The leftmost is S. Okay, these are all of the points I have in my data set. I'm going to change this picture every time I get a new HI. So this is sort of the global view, and this is the view that is seen only when predicting, only when designing H2.
So in the first case, uniformly sampling, you sampled all the points.
Maybe you had all the points, maybe you didn't have all the points, because you're uniformly sampling with replacement. With some probability, you will not see some of the points. With some probability, you will see multiple instances of some of the points. But most of them are going to be distinct. Right? But now, there's a high chance that these will be repeated. Okay? So now, let's say I design this predictor, and maybe the new predictor that I get is this one. This is a bad example, but whatever. Maybe I should have kept this point. Okay. So now I use ERM once again, and maybe the new predictor that I get is, say, this. Okay, so this is my H2B. Okay, let me also draw this H2B in this sort of global view. This is my H2B. Okay, so now let's look at what H2B did. It misclassified some of the points. All right. To be precise, it misclassified this point and this point. So now you tweak the distribution so that these points are sampled with a higher probability, but at the same time you sort of reduce the weightage to these points because they were classified correctly. It's still maybe slightly higher, but higher compared to S, but lower compared to S2. Right? Maybe I should not have. Okay. So let me take another copy of this. So now I get my S3 where say these points are given as slightly less than S2, but these points now get a slightly higher probability of sampling than P2. Okay, so now I get my new P3 and now I resample. Okay, some of these points that were missed in this case may appear here. So some points may appear, maybe in when I draw the sample, when I draw S3, some of these other points may not appear. Okay, so now I get a new classifier. So now I again train a new classifier. Maybe I get this point. To the left, right? Yeah, that's fine. Let's say that this is what it looks like. Okay. So this is my H3. And let's say that this is maybe I want to move H1 a bit to the right. This a little bit to the left. Right. Whatever. I mean, this is H3B. You get something. Now I have these three classifiers, and now I take a linear combination of these three classifiers. So maybe at the end, my final classifier is going to give some linear combination of these, and therefore it may label, let's say, this region as +1, this region as +1, this region as +1, and everything else -1. are kind of based on their individual performances. Yes, I'll give the explicit algorithm, but this is at a high level how it works. Okay, this is sort of the high level procedure.
It's just like decision trees. They're getting different partitions in the
Sort of, yes, but I mean, originally all of this AdaBoost was designed with a focus on decision trees, but this is much more general. Okay, and in fact, this can be generalized even further. Okay, so this is one sort of interpretation of boosting. And in fact, it's an interpretation of one very specific algorithm called AdaBoost. So let me give the algorithm.
So theoretical, just reasoning why it increases the chance of being classified is just because it is contributing more to the loss the next step.
Yes.
That's why it increases.
Yes. Okay. So now the AdaBoost algorithm is the following. So we are given a training set which is x1, y1 up to xn, yn. We are given a base class B. All right. So the first is step 1. You draw. Okay. So first you set P1 of xi to be equal to 1 by n for all I equal to 1, 2, 3 up to n. So this is the starting distribution, which is just the uniform over the samples. Say T. So let's say that we are running the AdaBoost algorithm for T rounds, capital T rounds. In the Tth step, you take HTB to basically be the ERM for on. Okay, so first you let's say you sample according to, let's say, S1. So you would implement essentially you sample S1 according to the distribution P1 and you obtain H or ST according to PT, and HT is ERM over the dataset ST. Since you know the distribution, you can compute the generalization error with respect to this particular distribution PT. So epsilon T is the probability where I is distributed according to, or xi is distributed according to PT of HTB of xi not equal to yi. So you can compute the probability of error with respect to PT, because you know PT, right? And then you set alpha t, this whatever constant this is, alpha t, to be equal to half log 1 minus epsilon t by epsilon t, which is half log of probability of being correct divided by probability of making an error. You set zt to be equal to 2 times square root of epsilon t into 1 minus epsilon t, and then you update pt, so pt plus 1. Up to n, or whatever, just set pt of xi is equal to, or pt plus 1 of xi is equal to pt of xi into e to the power minus alpha t yi h tb of xi divided by zt for I equal to, for all of the data points. So you now modify the probabilities of all of the data points according to this particular rule. And at the end, once you finish running all of these steps, you output h hat, which is sine of summation t equal to 1 to capital T of alpha t h tb. So this is the final predictor.
So shouldn't that be ET should be expectation?
Epsilon t,
Yes.
it is an expectation, right? I didn't get that.
We have probability.
That's because it's expectation of the 0-1 loss, which is just probability, right? In general, it's going to be the expected loss according to the distribution PT. So right now we're only focusing on binary classification with 0-1 loss. That's the problem that we want to solve. For a more general problem, it would be the expected target loss, but according to this distribution. Okay. So this is a rule, all right? It's a little mysterious, the choice of many of these things. It's not obvious why you're choosing, let's say, alpha t to be equal to this, or zt to be equal to this, or even the modification rule for pt plus 1. Correct. So that's basically, that's the high level intuition. That is essentially, okay, one thing to keep in mind is alpha t doesn't depend on the sample.
Each of them are different samples, but on that it was more confident.
No. So epsilon t is the average probability of error over the entire sample data set, right? So since we're assuming that we have a weak learner, epsilon t is guaranteed to be strictly less than half, right? And consequently, alpha t is guaranteed to be strictly greater than 1. I mean, okay, 1 minus epsilon t by epsilon t is guaranteed to be strictly greater than 1. So alpha t is strictly positive. Okay, so this is irrespective of, in a sense, alpha t is large if the probability of error of the predictor, the average probability of the predictor is small. So therefore, it's a good predictor for your overall data set. So that's why you give it a higher weightage. But at the same time, if you look at how this distribution is being modified, as I was referring to, you give higher weightage to those samples which are classified incorrectly, right? So suppose that this was classified incorrectly, which means that ht of xi differs from yi. So if that happens, then this product would be negative, which means that this exponent would be positive, and therefore this weightage has now increased. If you classified it correctly, then basically this would be positive, right? Because yi would be equal to ht of xi, therefore this product would be +1, and therefore the exponent would be negative, and therefore the weightage is now reduced. Right? So successively you're increasing the weightage for points that were misclassified in the previous step and lowering the weightage for those which were classified correctly in the previous step. Right? So intuitively this is how it's behaving, how this particular algorithm is behaving. And Zt is essentially just a normalization factor to make sure that this is a valid PMF. Right? This is very specific to AdaBoost. By changing these rules and by changing how you choose alpha t, you get a large number of variants. Okay, and we'll see sort of a systematic interpretation of all of these variants. Sorry, the loss of an ERM. If it's binary classification, it can be, but then you can essentially improve it to get a loss of less than half.
So isn't that assumption that we have chosen the base class as that we can compute the each other efficiently?
Yes.
So we are assuming that since you are able to compute each other at every step, this is guaranteed to have a loss or a risk less than half.
Strictly less than half.
Strictly less than half. So that's an assumption. Right?
That's the assumption. I mean, but the question was, can a particular predictor give a loss which is strictly greater than half?
So in that case, wouldn't reverse the outputs of your...
Exactly. You just reverse the outputs and you automatically get something which is less than half.
So then you could always have alpha to be...
So really the bad case is when it's equal to half. Right? The worst scenario is not when the loss is greater than half. That you can just modify to by flipping the outputs in the context of binary classification. The worst case is when the loss is equal to half. So if it's equal to half, it means that you're just guessing randomly.
So we should not reverse that, especially if you are testing on validation.
I'm sorry?
We should not flip that outputs, especially if it's on validation. Because it was doing well in training, like 90%, but
Yeah. I mean, this is in a different context.
over the validation training is same like
Yeah, let's suppose that it achieved a training loss of greater than half. All right, then you can just flip the outputs to get something that's less than half. Okay, that aside, so this is the algorithm. Okay, hopefully there are no questions. So the question is, why is this good? Can we quantify the performance of this algorithm? The claim is that if you look at the empirical risk of H hat or the original training data set S, right? As you increase the number of samples, as you increase the number of rounds of AdaBoost, this goes to 0, and in fact this goes to 0 exponentially in the number of rounds, minus 2 gamma square t. Right? Now this is a statement purely about the empirical risk. It doesn't say anything about the generalization error. But this was something that we could not do at all. Right? The base hypothesis class was such that you can only do slightly better than half. But through this process of combination, you can make the empirical risk as small as you want. Right? And assuming that doing empirical risk minimization on the base hypothesis class incurs very, very low time complexity, the overall time complexity of this AdaBoost procedure would just be t times the time complexity of finding one ERM in the base class. Right? The proof of this claim is fairly simple. So let's do that, and at the same time also look at this update rule a little more carefully. Right, so let's take a look at pt plus 1 of xi. This is equal to
What is gamma here?
so we're assuming that we have a gamma weak learner, right?
That's
So
it.
yeah, that's the gamma.
That's not design code.
Yes. So basically we're assuming that essentially each epsilon t is less than or equal to half minus gamma. That's the gamma. For every t, epsilon t is less than or equal to half minus gamma. Okay. So let's look at pt plus 1 of xi. So pt plus 1 of xi is e to the power minus yi times htb of xi divided by alpha t. Times pt of xi divided by zt, which is so first let's try to see why zt is exactly equal to 2 times square root of epsilon t times 1 minus epsilon t. So what is zt, or let's see what is zt plus 1. Zt is simply summation over all I of e to the power minus alpha t yi htb of xi times pt of xi. It's just the normalization constant, right? Because we want this to be a valid PMF. Now what I can do is I can split the i's into those which were correctly classified by HTB and those which were incorrectly classified by HTB. Right, so it's summation overall I such that HTB of xi is equal to yi of e to the power minus alpha t yi HTB of xi times pt of xi plus summation overall I such that HTB of xi is equal to minus yi, because yi and HTB, they only take values plus 1 or minus 1. E to the power minus alpha t yi HTB of xi pt of xi. So this is equal to so in this case this is equal to plus 1, right, and here this is equal to minus 1. So this is simply summation overall I that were classified correctly e to the power minus alpha t pt of xi plus summation over all I which were incorrectly classified e to the power plus alpha t times pt of xi. But I can take e to the power minus alpha t outside because it's independent of I, right? So this is e to the power minus alpha t times summation over all I such that xi was classified correctly of pt of xi, which is simply the probability of correct classification. Plus e to the power plus alpha t times the probability of error, which is nothing but e to the power minus alpha t times 1 minus epsilon t, because epsilon t is the probability of error, plus e to the power alpha t times epsilon t. But what is alpha t equal to? Alpha t is equal to half log of 1 minus epsilon t by epsilon t. So this is equal to square root of epsilon t by 1 minus epsilon t times 1 minus epsilon t plus square root 1 minus epsilon t by epsilon t times epsilon t, which is nothing but 2 times square root of epsilon t times 1 minus epsilon t. Okay. So if I look at product, say t equal to 1 to capital T, zt, this would basically be equal to product t equal to 1 to capital T 2 times square root of epsilon t into 1 minus epsilon t, which is t equal to 1 to capital T square root of 1 minus just sort of completing the square. This is 1 minus 4 times half minus epsilon t the whole square, which just by simply using the bound on exponentials.
So,
Yeah.
which is why are we doing this?
Which one?
Why are we deriving this?
I want to prove this particular claim.
So this is the part of that.
Yes.
Because I just wrote the expression of RSH, R empirical is coming.
Correct. So we'll get to that, but but in order to show that this is less than or equal to this, and also let's also try to get some of the steps and understand what is happening to each of these terms. All right. So eventually I'll get a term which involves product of all of these zt's. So I want an upper bound on this particular quantity. Okay. So this again sort of straightforward upper bound in terms of the exponential. This is less than or equal to e to the power minus 2 t equal to 1 to capital T half minus epsilon t the whole square. Okay, fine, we have something. All right. So now let's look at okay, and the reason why this is important is let's look at pt plus 1 of xi. This is equal to e to the power of minus yi minus alpha t yi htb of xi divided by zt pt of xi, but again express pt of xi in terms of pt minus 1 of xi, which gives me a recursive relation. Sorry, gives me a recurrent relation, right? So this is e to the power minus alpha t yi htb of xi divided by zt times e to the power minus alpha t minus 1 yi hi of xi divided by z t minus 1 times pt minus 1 of xi, and I can go on, right? So this is equal to e to the power minus yi times summation I, let's say L equal to 1 to t alpha L HL B of xi divided by product L equal to 1 to t of ZL times P1. But what is P1? It's the uniform distribution. So it's 1 by n. And if you look at it carefully, this is basically my, okay, let's look at RS of H hat. All right. So RS of H hat is basically 1 by n summation overall I indicator yi times sine of summation little t equal to 1 to capital T alpha T H T B of xi. This is less than 0 or less than or equal to 0, which is the same as 1 by n summation overall I indicator yi times summation t equal to 1 to capital T alpha T HTB of xi less than or equal to 0. Right, because anyway we're looking at just the sign. If yi times the sign of this is negative, then yi times the quantity itself should be negative. Right? This can happen only if and only if this is negative, then this is negative, and vice versa. Now, a fact that we're going to use is that the 0-1 loss is upper bounded by the following exponential loss. So if I take summation I equal to 1 to n of e to the power minus yi summation t equal to 1 to capital T alpha T HTB of xi, right? Because if you plot the 0-1 loss, for parameter u, the 0-1 loss looks something like this. It's equal to 1 if u is negative and 0 if u is positive. And e to the power minus u looks something like this. Right? That's all that I'm using. So indicator u less than or equal to 0 is upper bounded by e to the power minus u. But this quantity, this e to the power minus yi times this is exactly the quantity I have over here in the numerator. Right, so this is equal to 1 by n summation over all I n times pt of xi, sorry, pt plus 1 of xi times product I equal to, t equal to, t prime equal to 1 to t of zt prime. Right, I've just used that this quantity is this quantity times this. Okay, but I've also derived an upper bound on this quantity. Right, so that product that I derived over there, we saw that it's less than or equal to e to the power minus 2 times summation over all of this. So this is less than or equal to 1 over n summation over all I n times t plus 1 of xi times e to the power minus what was it, 2 times summation t equal to 1 to capital T of half minus epsilon t square. Right, this n and n cancels, and this the sum overall I pt plus 1 of xi is equal to 1. So this is equal to e to the power minus 2 times summation t equal to 1 to capital T half minus epsilon t the whole square. But we assume that at each step we have a weak learner, a gamma weak learner, which means that this quantity is at most gamma, or half minus epsilon t the whole square is at most gamma square. So this is less than or equal to e to the power minus 2 times t times gamma square. So as you increase the number of rounds of AdaBoost, the training error goes to 0. So basically, we started out with a weak classifier that just did slightly better than random guessing. And through an iterative process, we now came up with a new classifier which achieves a vanishingly small training error. So in the next class, we'll interpret AdaBoost in a slightly different way as a coordinate descent of some particular loss function. And that interpretation gives rise to an even wider class of algorithms called gradient boosting algorithms. All right, so let's stop here.